All right, let's go ahead and get started. Welcome to the second session in a webinar series designed to advance climate change adaptation in protected areas through the exchange of information between practitioners in Eastern and Southern Africa with staff and colleagues of the United States National Park Service Climate Change Response Program. My name is Melanie Wood with the Climate Change Program based out of Fort Collins, Colorado, US, and I welcome you all to this session today. Before we get started, this webinar is being recorded and will be made available to you later. I'd like to direct you to please mute your audio under the microphone icon on your Zoom control panel when you are not speaking. We hope to have dynamic communication between our speakers, our hosts, and our attendees during our session through features like the chat box on your Zoom control panel. So I encourage you to take time now to find that chat box. Please ask us questions and make comments as you wish, and I will be asking you questions both in the chat and through an upcoming polling feature. If you're having issues with your audio or internet connectivity, you can chat your host directly by clicking on the chat, find the three little dots to the right of your message box, and select hosts and co-hosts, and one of us will try to help resolve the issue. We will drop some additional guidance on internet connectivity in the chat now. We have two presentations today, and we will hold most questions until the end, but I again invite you to post questions and comments in the chat throughout the presentations. This will encourage active engagement throughout the session. We have several co-hosts for this series, but a couple that are helped to kick off our series today is Fatsimo, the Regional Environmental Specialist for Southern Africa, based at the U.S. Embassy in Gaborone. Joel Reynolds, Climate Change and Adaptation Coordinator with the U.S. National Park Service Climate Change Response Program based in Fort Collins, and Larry Sperling, Senior Advisor, Office of International Affairs, U.S. Department of Interior, based in Washington, D.C. We invite our co-hosts, Fatsimo and Larry and Joel, to turn on their cameras, and I will turn it over to Fatsimo and Joel to introduce the why and how of this webinar series. And then we'll engage in some brief introductions and get started with our speakers. Fatsimo.
Hi, Melanie. Hi, Joe. Hi, everybody. I'm Fatsimo Kwenani. I'm the Regional Environment Specialist for Southern Africa, working for American Embassy. And I want to take this opportunity to thank you all for allowing me the opportunity to welcome our participants to this series of 22 over 10 of our webinar. Please allow me to say protocol is being observed. I want to take a moment to express my sincere appreciation to all of you in finding time and bandwidth, both figuratively and literally, to register for our second of 10 webinars we are supporting with the U.S. National Park Service regarding climate change adaptation on protected area management in Southern and Eastern Africa. This is actually part of the U.S. State Department's Embassy Science Fellow Program, which provides our embassies around the world access to the expertise of the U.S. government offices in the science and technology space. So in other words, this is a matchmaking program. Today, we are excited to be talking about climate change, challenges and approaches to the freshwater management in protected areas. And being born and bred from Southern Africa, specifically Botswana, I have seen firsthand challenges to our freshwaters due to the change in climate. I have witnessed how our countries are encountering and adapting our practices and our resources to the impact of climate change in our areas of responsibilities. As we know, Eastern and Southern Africa are expansive regions with unevenly distributed water resources compared to population and settlement patterns, coupled with a variable and changing climate. Water variability and water quality are critical concerns to this region, and climate change will even increase the hydrology and weather parameters, variably causing frequent and intensity, rainfall magnitude, and trends to reach to the extreme situations in our region. The severity and the frequency of droughts, floods, and storms will increase, leading to more water stress. These are not just unique to our Eastern and Southern African regions. Scholars also tell us that South Eastern and Gulf of Mexico in the US is not spared from the climate change effects. Many of the expected climate effects there will exacerbate current anthropogenic stress on the region's freshwater system, including demand for water, increasing waste heat loads, land use changes, and water the quality and quantity of runoff to streams and reservoirs. And with this, responding to the climate change will require adaptive institutions and infrastructure built to accommodate and operate effectively under the range of condition. I would also want to take this opportunity to just share a little bit on the US efforts on water. The US goals are to support a water secure and world where they have sustainable supplies of water of sufficient quality and quantity to meet the human, economic, and ecosystem needs while managing the risk from floods and droughts. And to achieve this goal, the United States will provide technical assistance, make targeted investment in sustainable infrastructure and services, promote science, technology, and information, mobilize financial resources, engage diplomatically, and strengthen partnership and intergovernmental organization. The United States remains one of the world's largest donors in the water sector, investing in capacity building, infrastructure, technology, private sector engagement, and innovative financial instruments to mobilize local capital. One may ask, what has the US done so far? What has the US invested in the water sector? Examples will include, in 2017, our USAID provided $449.6 million to support water, sanitation, and hygiene activities in 41 countries. And again, in the same year, USAID invested over $706 million in water-related investment, including development funding and humanitarian assistance in the wash sector, as well as water for food, water resources management, water productivity, and water-related disaster risk reductions in 45 countries. As of 2017, the Millennium Challenge Corporation, another US foreign aid agency, has invested more than $10 billion in clean water, sanitation, and natural resource improvement projects in partner countries in Africa, Asia, Europe, and Latin America. The Millennium Challenge Corporation also invested more than $776 million in water-related projects as of the end of the financial year 2019. With these achievements, I'm actually so excited to see all of you come together today and over the next 9 months to discuss how to best support the climate action adaptation in your protected areas. I look forward to listening to this fruitful discussion and also to watch you in building a network of contacts in your own country, your continent, and overseas, because no one can fight the climate change crisis alone. So again, I want to thank you for this opportunity to welcome you today to this second of the 10 series webinar for the climate change adaptation in the protected area management. Thank you so much.
Thank you very much. Good afternoon, everyone. Good morning, those of you in the States. This is Joel Reynolds. I just wanted to remind everybody a little bit about the upcoming sessions before we kick off, and then we'll go into today's presentations. As Batsimo mentioned, let's see, hopefully the screen share seems working. All right. As Fatima mentioned, this is the second in a series of 10. The selection of topics was based on some earlier discussions with staff in the CASA Secretariat and with Sandpark staff. And then we've sequenced the topics basically based broadly on the steps you have to follow as you move through trying to advance climate change adaptation. So last month, we had presentations on climate change vulnerability assessments. We have a recording of those, and we're resolving a place to host those recordings, but we'll share that link out as soon as that gets resolved, hopefully in the next couple of days or so. Today is digging in more on some of the technical issues associated with freshwater management, and really about thinking about resource climate sensitivities and future impacts stemming from the vulnerabilities. Next month, we're going to have sessions based around scenario planning and basically accounting for uncertainty in future climates and developing adaptation strategies. In April, the Resist, Accept, Direct framework, which is a framework for helping structure brainstorming around adaptation strategies. And then from May onwards, moving a little bit more into sort of landscape scale collaboration topics. So if you're interested in possibly speaking or sharing some of your work on any of these topics, please send an email to either the easiest way would be to send an email to the address that Melanie has already put in the chat at climatechange@nps.gov. That would be great. The other point I want to make, I forgot to, you can send an email to me or the one that I just put, that Melanie put in the chat. The other thing I want to remind you about is that these sessions are all going to be on the last Wednesday of each month. Recordings will be made available, and we'll announce the speakers and abstracts roughly 3 weeks in advance of that. With that, then Melanie, let's see, let me quickly check where we are. All right, back to you, Melanie.
Thanks, Joel. Okay, so before we get started on our presentations, I'd really like to hear a little bit from you and encourage you to get to know us and each other. So if you could, invite you to introduce yourself in the chat box by typing your name, your position title, organization, and the country you are joining us from today. And I will start to drop my name, Melanie Wood, Project Manager, Climate Change Response Program, USA, in the chat. Please go ahead and drop your information in there as well, as sort of by way of introduction to each other. And while we're doing that, I would love to introduce just a couple of quick polls. So if you're sitting at your desk, you should see a screen pop up that asks a pretty simple question, which is just, what is the best description of your organization? You should see that pop up now. Are you from some kind of protected area, some sort of provincial or district or non-US federal agency, academia, nonprofit, another stakeholder organization, US government? We have several of those on the line today, including myself. Are you a student? So those responses are coming in now, and I'm going to give it a couple more minutes. Welcome to the folks in the chat. Thank you for joining. We've got South Africa, Mozambique, USA. Whoa, David Thoma says it's negative 30 degrees Celsius this morning in Montana. Zambia. Okay, I think we've got everybody in the poll. So I'm going to end this poll and share the results. And there we have it. We have several folks from TFCA, National Park, or other protected area. Welcome. Thank you for joining, as well as pretty nice distribution of other folks. So I'm going to ask one more question. And that is getting at the idea of, why are you here? Most important thing I'd like to learn about in this series overall, not just today, but the whole next 10 months we have planned. Are you looking to learn about what other organizations are doing, discover new tools you can implement in your work, identify new partnerships, fill knowledge gaps in your organization, or prioritize your next action? So thank you for entering your response in this poll. I'll give it a few minutes, or a few seconds rather. I'm looking at the chat now. Welcome to everybody who's just posted. Okay, I'm gonna end this poll in 3, 2, 1. And here are the results. Looks like the majority, not the majority, but the strongest answer is we're here to learn what other organizations are doing. So let's get on with that now. I'm going to stop sharing the screen. Close out that box on my end. So thank you very much for participating in these exercises. We really want to try to make this a little interactive. So please continue to enter comments and questions, anything you're thinking about today, maybe the temperature outside of your house. Sounds like it's really hot in some places and really cold in others. And then we're going to go ahead and turn it over to Joel to introduce our first speaker.
All right. Thank you, everybody, for sharing a little bit of information about yourselves. That's helpful to know who's here. As we begin the main presentations, I want to remind everybody to please mute your lines if they're not already. And feel free to raise questions for speakers in the chat, and we'll compile those and then go through them in the discussion. All right, so our first speaker is Dr. Eddie Riddell. He applies his background in ecology and environmental hydrology to his work as water resources manager for Kruger National Park, where he strives for strategic and adaptive water resource management for sustainable catchment management and benefit sharing. He uses a collaborative stakeholder-based approach for scientifically and technically informed engagement of water resources management in order to maximize benefits for aquatic ecosystem conservation in Kruger. Prior to joining South Africa National Parks, Dr. Riddell completed his PhD and postdoctoral fellowship at the Center for Water Resources Research, University of KwaZulu-Natal, with a focus on wetland rehabilitation, groundwater, surface water interactions in ephemeral catchments, river operations and governance in the Nkomati River Basin. He's a registered professional natural scientist and maintains an academic record through scientific research, publication, and postgraduate supervision. And so Dr. Riddell is in Kruger running a workshop right now. So he's recorded his presentation and we're gonna play that now. He's on the line to join us for questions when we get to the discussion section. So with that, let's go ahead and start watching the recording.
Okay, the first couple of seconds of this video, I'm going to play and then pause to make sure you can all hear the audio. This is a new experiment for us. Here we go.
Hi, good day, everybody. My name is Eddie Riddell.
Did you hear Eddie introduce himself?
The audio came through, Melanie. It sounded a little low. So we might just encourage our participants to ramp up their own volume if necessary.
Okay, I'll try to turn everything up on the side. I don't know if that will do it or not. Okay, thank you.
Water Resources Manager in the Kruger National Park, South African National Parks. And I have pleasure today giving you a talk for the information exchange with protected areas of Eastern and Southern Africa, focusing particularly on the freshwater ecosystem effects of climate change on the Great Limpopo Transfrontier Park. To start off this presentation, I'll give a bit of a perspective around climate change in terms of the protected area state that South African National Parks manages, and then moving on to a description of the Great Limpopo Transfrontier Park, and then some impacts of climate change that we know for the region, particularly from a water resource management perspective, and some cross-cutting themes through several examples where we look at the adaptive governance options and some of our contemporary challenges, rounding off with some thoughts around water security for the protected area network. South African national parks manage a protected area network of over 20 national parks presently. You can see the map of that in the bottom right-hand corner. And colleagues of ours did a climate change risk analysis for the protected area network a few years ago, and this included looking specifically at the state of the freshwater ecosystems in the country and their level of protection under formal protected area networks. So they identified that basically half of South Africa's rivers, wetlands and lakes are ecologically modified in some form, and similarly half of the river ecosystem types represented in South Africa have no formal protection in protected areas. They also identified that only a small proportion, about 2.9%, are formally protected within national parks, although that increases to about 8.2% when you consider the entire formal protected area network that's under provincial and private custodianship. Within the protected area network itself, the good news is that 64% of rivers are actually in pretty good condition. They have a high ecological category. And there's also been a concerted effort in recent years to take a closer look at the wetland assets within the national parks. So that is currently work in progress. So for the remainder of this talk, I'm really going to zoom into the northeastern region of South Africa, primarily around the Kruger National Park, which is our largest protected area. It's over 2 million hectares, and that in itself forms part of the Great Limpopo Transfrontier Park, which is shared between the republics of Mozambique and the Republic of Zimbabwe. We have a number of, or quite a large diversity of freshwater ecosystems. We also straddle two very large river basins, namely the Inkamati in the southern region and then the Limpopo Basin in the north. And we also have Ramsar sites in the northern reaches of the Kruger National Park, the Makulek Ramsar wetlands. You're welcome to click on those links at the bottom if you want to get a bit more understanding around these two protected area networks. But the overall philosophy that we manage our natural resources, and this is particularly pertinent to the freshwater ecosystem management, is we recognize that these parks are embedded within a broader landscape. So the river systems and the drainage network and the freshwater ecosystems are critically dependent on what happens upstream and increasingly what also happens downstream. So when we manage for these ecosystems, we take a holistic view in terms of ecosystem approaches, but also recognizing that this is also part of a broader socio-ecological system. Given this talk is about climate change and climate adaptation, it's probably useful to just put up this refresher. I'm sure most people have seen something like this before, but it's around the representative concentration pathways around global CO2 emissions. And it basically shows you, according to different scenarios around carbon emissions into the atmosphere, tracks different trajectories. And at present, whether we're just looking at the fossil fuel perspective on the left-hand side or the total CO2 emissions that come about through fossil fuel emissions and land conversions and other activities, we're quite close to the higher trajectory at present. So it is a slight cause for alarm, but obviously the world is also starting to move in different ways. But the present trajectory we've been managing our systems over the past couple of decades is really actually along this RCP 8.5 curve, which is unfortunately the worst case scenario. Given the context of global carbon emissions on the previous slide, it's useful then to zoom in to provide the temperature context for South Africa compared to the global average. And what the Climate Systems Analysis Group at the University of Cape Town has shown is that actually South Africa is experiencing double the warming as compared to the global average. So this is quite significant when you think about what that means for the availability of fresh water, the utilization capacity of fresh water, and therefore the impacts on freshwater ecosystems. So what does this mean for consequences in terms of managing, protecting and conserving freshwater ecological systems? Well, we're fortunate in South Africa, we have some of the world's leading freshwater scientists as well. And one particular study was conducted by Dr. Helen Dallas and Dr. Nick Riversmore in 2014 that took a holistic assessment of the impacts of climate change on freshwater ecosystems for the whole of South Africa. Clearly, the freshwater ecosystems are vulnerable to climate change effects, and in particular the aquatic organisms that live within those freshwater ecosystems. Some of the impacts of that is things like alien species invasions, extinctions, redistribution, loss of ecosystem function, changes in river connectivity, and so forth. But what the authors advocated there was to really use proactive management in the management of these freshwater ecosystems under variability, but then more importantly under climate variability. So they advocated for proactive management, and they realized that the South African policy environment allows for this. So allowing for proactive awareness of changes in river systems rather than being reactive, because obviously once things have happened too late, it's very hard to restore any ecological condition and ecosystem service. But amongst the threats that they identified, you don't need to worry about this table, there's quite a lot going on. But what I want to do over the series of slides moving forward is basically highlight some of the key things we're starting to see in terms of the viability of the freshwater ecosystems within the Great Limpopo Transfrontier Park. For practical purposes, our freshwater management really utilizes what we call strategic adaptive management. And this also applies to a broader range of other ecological assets we manage within the protected area network. But it's gained real traction in the freshwater focus. It's a subject that could make a much larger lecture, so I'm just going to very quickly summarize what strategic adaptive management is. It's basically about learning by doing. We recognize that we're managing natural systems, and those natural systems are dependent on variability. And within that, we develop what's called thresholds of potential concern. So these are relative indicators that allow us to track change over time according to this framework. So we set a desired state for our freshwater ecosystems, and we set a long-term goal, trying to achieve perhaps a new recommended ecological category, which would be our desired system. But we realize the way to get there is not a straight line. You know, we're going to have to take tacks and turns in order to get to that new desired state. And often when we get to that point in the future, 5, 10, 20 years down the line, the desired state might be slightly different. So we're managing for that variability. There's been a lot of work that's been done on strategic adaptive management. It goes almost all the way back to the 1980s, starting with the Kruger National Park Rivers Research Program, and was then embodied in policy in the 1990s, and then really put into practice, particularly around environmental flows in the early 2000s and the 2010s. But what it does, it allows us to reflect on what we're doing. It allows us to inform, for example, the monitoring of the river system or the wetlands. And if those thresholds are not working to meet those desired ecological outcomes, we can review those changes every so often. And what's important as well is we can also reflect on the policy requirements to achieve those objectives. So what does this mean for the availability of water resources that these freshwater ecosystems depend on? Well, fortunately, there's been quite a lot of work that's been undertaken in recent years looking at this from a climate change perspective. And one of the most recent examples comes from Professor Roland Schultz's work with his team, utilizing the ACRU model and applying it across South Africa using a range of global circulation models that give you a climate change forecast over the next 100 years. And this national scale assessment was done to quite a fine scale, what we call quaternary catchments in South Africa. And what it points out is overall this map. There's basically winners and losers. So for the vast majority of the country, we're going to see quite a severe decline in stream flow generation and therefore availability of water resources across the country. But in some regions there are winners. So the western region might get a little bit wetter, and then parts of the northeast region might also get a little bit wetter, but particularly this area in the far northeast, where the Kruger National Park is probably going to get drier. So what does that actually mean for impacts upstream? So what that means is we might get a 4 to 12% increase in the irrigation requirement. And upstream of the Kruger National Park, there's quite significant irrigation development and some very large national irrigation schemes. Zooming in a little bit more in terms of the catchment level, what that means is, again, in some headwater areas we might get fewer dry spells, but the areas closest to the Kruger National Park, we're probably going to see an increased frequency of dry spells. So starting with that national scale assessment, I'm going to zoom right into the Kruger National Park area, and particularly the Olifants River catchment, which is the largest catchment that drains into the Kruger National Park and is the main tributary of the Limpopo River. So Pollard and Retief in 2020 did a review of all the analysis that has been done in the region, including the short study, and basically came up with some conclusions around what's coming out of these various studies on climate change effects. So they're pointing out for this particular catchment, we will see an increase in temperature of 1.7 to 4 degrees by mid-century, by 2050. That combined with the effect of evaporation, which I mentioned around irrigation demand, for example, we'll see a predicted decrease in stream flows of even up to 60%. And therefore that also then means a reduction in the yield of our large storages upstream of the Kruger. It should be pointed out that the Olifants River system is probably our most stressed river system. A large number of our sensitive taxa, macroinvertebrates and fish have been removed from the system, as indicated by this correlation matrix against water quality parameters. But that's through historical. South Africa's policy environment allows for the implementation of environmental flows, known locally as the ecological reserve, and this is the only right to water along with basic human needs. So when we apply this to our river system, we certainly want to avoid this kind of scenario where we see a significantly large perennial river system dry up, as we saw back in 2005. Well, what does this mean in times of drought? Well, we recently experienced a drought in 2015-2016 due to an exceedingly strong El Nino. And this data shows you the long-term climatic record for Skukuza in the central part of the park. And it shows that against mean annual precipitation, we often get a 7 to 10 year cycle of significantly below average rainfall. But during 2015-2016, this was a double year event with exceedingly low rainfall. On top of that was the temperature. So if we compare it to the previous drought of 91-92, in all months we had much higher numbers of days above 35 degrees. And similarly, the occurrence of a large number of days above 40 degrees. So the conditions were quite distinct from previous droughts. In South Africa as a whole, the whole country experienced a drought, but as you can see here, putting the strategic adaptive management process into practice involves us working very closely with upstream users and upstream water actors, notably our catchment management agencies, our irrigation boards and dam managers and so forth, but increasingly starting to report on these actions in terms of environmental flow implementation and water quality effects to our downstream neighbours in Mozambique. Given the context just presented, you might be wondering what actually happened to the Olifants River in 2016. Well, we experienced very, very low flows down to below 1 cubic meter per second in January of 2016. This should be the height of the rainy season. This was also impacting on the ability to deliver water to our large water board, Lepele Northern Water, who are situated here at Phalaborwa, as well as the large agricultural sector, also dependent on usage from the Bladder Dam. So together with our NGO partners, the Association for Water and Rural Development, funded at that time by USAID, we approached the Water Affairs, who were themselves overworked because it was a national state of disaster. And we suggested that we could work together with NGO partners and local partners to ameliorate the problem. And fortunately, that request was approved by the Director General, and we then set about to establish a committee and develop what we call interim operating rules for the system. And basically, and as a result, we were able to track this using our TPC system, which I mentioned earlier. These are the worry levels around our flow, the red being our reserve requirement. And you can see during the drought, we were barely meeting that at all, and the river was coming close to drying up. We also had a river management logbook, which allows for transparency in the decision-making utilized during that event. And we continue to use this system in all our river systems. With the result that this is a flow duration curve, it shows that the river performance was significantly better than in the previous drought, and the river effectively dried up in 91-92, but we were able to keep the river flowing. If you want to get some more details about that particular case study, please refer to this report highlighted here. I'm going to move further to the north of the park, up to the Makalak Ramsar wetlands, right in the top part of the park. This is part of the Limpopo-Luvuvu confluence area, and speak a little bit about the temperature effects we started to notice in recent years. So this is colleagues from the University of Venda in November of 2020, and we started to see in the floodplain area, as the river comes out of a well-mixed gorge, we're seeing water temperatures about 36 degrees. This was on a 44 degree in the shade day down in that area. With the result that we started to see the die-off of several fish species due to excessively high temperatures. And we've seen this event repeat itself over the past 2 or 3 years. So it is a cause for concern. But having said that, it's a river that we also implement environmental flows. And this is looking downstream into Mozambique. The Limpopo River system was dry at that time, but the implementation of environmental flows allowed in the Lavuvu system allowed contributions into the Limpopo. And this was an exceedingly hot day, and we saw people coming from Mozambique on the right hand side, as well as Zimbabwe on the left hand side, enjoying the river system at that time and utilizing its water resources. So it's a really good example of implementing environmental flows for socio-ecological benefit in a large protection. I've spoken quite a bit about drought conditions, but what about the reverse? We are also in a cyclonic area, and probably the most well publicized is the 2000 floods, which affected Kruger National Park and Mozambique. But we've seen an increased frequency of cyclonic activity over the past few years, as recent as last year with Cyclone Eloise, which made landfall and had some significant impacts. The impact of these cyclones can be seen on the image on the right hand side, which is the Sabi River as a result of Cyclone Eline in the year 2000. You can basically see that it scours out the entire riparian zone gallery forest, and obviously there's been a lot of work that's been done on the impacts of that over the past 20 years. One of which is LiDAR based work and geomorphic modelling by Midland and Heritage and colleagues, and looked at the impacts of the 2000 floods and subsequent floods on various river systems in the park. And the 2012 flood itself, as a result of Cyclone Danda, removed 1.2 million tonnes of sediment. And it even removed a mature riparian forest that had actually survived the 2000 floods. What Milan has also shown is the frequency of these flood events has increased, likely as a result of climate change effects already. And what it means is that elements of the riparian forest and other habitat types in the Sabi River have not been allowed to recover. And basically suggesting that the increased frequency of these cyclonic events will continue to strip out the sediment and vegetation from the river channel. And often citing there's about a 100-year recovery period for the riparian zone succession. And they gave scenarios around what this would mean for a bedrock-derived state as well as an alluvial starting state. Some of the other effects we think can be attributable to cyclonic activity is the possible eutrophication and harmful algal blooms in some of our river systems that flow into large dams downstream of us into Mozambique. And we think this is one of the reasons why we had the pancytitis outbreak that affected the Nile crocodile population in the Olifants River in 2008. But this compounds other effects that we have on eutrophication in the lotic environment following extensive low flow periods, which I mentioned earlier around the Olifants River. So when we put in higher anthropogenic nutrient inputs, it's a compound effect that has led to some breakdown in the aquatic food chain in the lotic environment. So this again is the Olifants River, and just to point you into the location that we're talking about, this is the Massingier Dam. It's almost 3 billion cubes. It's a very large water supply system for Mozambique, and the Olifants River flows into a very deep gorge area just before it flows into the Massingier Dam. And as recently as 2021, we had a very extensive algal bloom in the dam that worked its way upstream into the park. And that was as a result of very protracted warm winter temperatures, which basically kept this algal bloom alive for over 6 months and put it in a... And this can be seen here. This is the river as it flows into the Massingier Dam, and it shows that the total available phosphorus in the river at that time was 960 parts per billion, which puts it in an excessively hypereutrophic state as mentioned. But based on this information, we were able to work very closely with our downstream counterparts in Mozambique and provide some early warning to the citizens that utilize the Massingier Dam for their livelihoods, because we picked up a very large presence of microcystin and therefore potential toxin risk from cyanobacteria. We also saw this effect in the Sabi River system, which you may recall I mentioned is one of our cleaner river systems as compared to the Olifants. We also saw this in 2021 into the Curumana Dam. Importantly, this dam is now supplying the city of Maputo in Mozambique, which is a city of 4 million people. So this was a great concern to our counterparts in Mozambique as well, with the presence of microcystin. Fortunately, it wasn't as hypereutrophic as we experienced in the Olifants, but still suggests an increased likelihood that we might. The issue of eutrophication of lakes and dams is getting a lot of attention globally as a result of climate change. So this is refers to some studies that have been done in temperate systems, but there should be an increasing focus on these tropical and subtropical systems as well. So this is something we're watching out for as the Great Limpopo Transfrontier Park, especially as we consider the ecosystem services provided by the protected area state to ameliorate some of these impacts as they flow into large storages downstream for the benefit of people that live downstream in neighbouring states. So I've focused quite a lot on the challenges we've experienced with climate change effects that we think might impact the protected area in the future. But there's also some potential positives. There's an emerging body of work that's looked at the groundwater recharge effects throughout the continent. So this applies particularly to large protected areas that we have in Southern Africa. It basically suggests that groundwater can provide some resilience in these semi-arid systems due to the long-term adaptation cycles and the significant potential for large recharge events as a result of, for example, cyclonic activity. So effectively, what we might see is in drought periods a large drawdown, but then these would be regularly topped up by the cyclonic activities. But we'd obviously have to compare what that means with the surface water hydrology, of course, and so that's a growth area for research. So there's a potential benefit for groundwater dependent ecosystems and also possibly the implementation of environmental flows, and we've been working with some partners to look at those potential benefits. The chart on the bottom right hand side basically shows you an example of our long-term groundwater monitoring data in the southern part of the Kruger Park. And you can see there's been a steady decline if we extrapolate that back to the year 2000, where we had a significant recharge event. So we've seen a steady drawdown over the past 20 years with a little bit of a top-up during 2013 to 2014, when we had cyclonic activity in the region as well. I've given a very quick overview of examples that we have experienced that would allude to the possible impacts of climate change on the freshwater ecosystems in the Great Limpopo Transfrontier Park. There's obviously challenges, but there may well also be some potential benefits. So the outlook is mixed. It's not entirely bleak, but it's an ongoing focus of our research within the protected area. There's some other items that I haven't had time to explain in this talk, issues that we're dealing with around alien invasive species, both fauna and flora, and other impacts like that. But I think on the whole, what we've learned over the past 40 years of the Rivers Research Program in the Kruger National Park and the GLTP is to increase our adaptation potential. It's really, really important to develop partnerships, particularly around stewardship, water stewardship, land stewardship upstream. We have a very good network of NGO partners and other groups that assist us to develop these landscape scale programs. So in addition to that, what we found is really beneficial is for us as protected area managers to be very much part of the networks with other water sector users, particularly when it comes to catchment management planning, so that we are able to inform that narrative as part of the climate adaptation planning for all users within a river basin. One of the emerging policy frameworks that we're starting to see within the SADC development community is the alignment of our transfrontier conservation areas coordinating quite closely with our transboundary water resource management entities known as the river basin organizations. So this, we're hoping, will cement some of that climate adaptation potential by looking at large scale policy frameworks that allow us to work cooperatively at larger scales. I want to thank you all for listening, and also to thank the US National Park Service for facilitating this webinar exchange with protected areas in Southern and Eastern Africa. I hope you found it interesting, and I'll be more than happy to take any questions you may have. Thank you again.
Excellent. Thank you very much, Eddie, for that. I do, if there's any very specific sort of clarification questions, I'd like to go ahead and take those now. Otherwise, I'd like to hold most questions for the discussion section. Is there anything very focused that people wanted clarification from Eddie before we move on to the next presenters? And you can just put that in the chat. Okay, well, I'm going to move on. Be thinking about the questions, and please go ahead and be adding your questions to Eddie into the chat, as well as we go into the next presentation, questions for Dave Lawrence and David Thoma. So let me introduce the next presenters. All right, so our next presenters are both from the U.S. National Park Service. Dr. David Lawrence specializes in aquatic ecology and has worked as a climate change scientist with the National Park Service's Climate Change Response Program since 2017, conducting and translating climate change research to support forward-looking land and water management. Since joining in NPS, Dave has developed and evaluated projections of changing hydrology within national parks, including changing flood regimes, groundwater recharge, and runoff, and supported climate-informed strategic planning with parks nationally. Dave's actively collaborating in efforts to support management of landscapes undergoing ecosystem transformation and to assess the adaptive capacity of species to climate change. Dave is going to be joined in the presentation by Dr. David Thoma, who is an ecologist with the Inventory and Monitoring Program for the Northern Colorado Plateau and Greater Yellowstone Network Parks of the U.S. National Park Service. He works with managers to develop adaptation strategies for coping with climate change. David has published on water availability and drought effects that can help guide conservation of desert springs, semi-arid rangelands, montane wetlands, subalpine forests, and alpine meadows. David looks to nature for answers and works with colleagues to find solutions that can help land managers steward protected areas through continuous change. David received his BS from the University of Arkansas, an MS from Montana State University, and a PhD in watershed science from the University of Minnesota. Again, while Dave and David are presenting, I'd encourage you to ask your questions in the chat box so that we can use those for structuring the discussion that will follow. All right, with that, I will turn it over to Dave Lawrence.
Okay, thank you for that introduction, Joel. Give me a moment here while I bring up my presentation. Let me know if you see the title slide of our presentation.
So we see sort of the PowerPoints. There we go. See the title slide now. Yes.
Okay. Excellent. There may be a slight delay, so I apologize for that. So thanks for that introduction. And David Thoma and I will today be speaking about some water balance applications for climate sensitive resources, freshwater resources within national parks. And to start, my slide will advance. One moment. Okay. This covers the topics that we'll be talking about today. We'll start by just a broad overview of some of the freshwater resources within the U.S. National Park system and talk about some of the water resource challenges related to climate change, and also speak to how we think about planning for climate change within the Park Service, namely using the Climate Smart Conservation Framework. Then we'll transition to talking about using water balance as a tool to help assess the sensitivity and exposure of resources to a changing climate, both in the terrestrial and freshwater domains, but we'll focus primarily on the freshwater applications, given the general focus of this webinar. And then we'll zoom in specifically to some use cases of applying water balance to evaluate the vulnerability of both natural resources and infrastructure within national parks, and then we'll wrap it up with some conclusions. So just to give you a broad overview of the U.S. National Park Service system, there are 423 parks that are represented within 50 states, as well as the U.S. territories. It covers 34 million hectares or 85 million acres. And those parks are represented by both the larger parks are more visible via the green polygons, but smaller parks are represented by their centroid across this map. And you can see the broad distribution of parks. And then I just wanted to just show some pictures of the broad array of types of systems that the U.S. National Park Service contains and is charged with managing. And of course, since we work within a park system, it's always nice to look at some pictures of what these places look like. So just a few examples here. For example, the Cypress National Preserve. It's basically a swamp area within the bottomland hardwood forest within the Florida area. And then if we move to the northeastern United States, this is a picture from Acadia National Park in Maine, where managing both lake systems as well as the coastal system. And if we move into the western United States, this is a picture from Dinosaur National Monument, which spans Utah and Colorado. These are some desert river systems, including Grand Canyon National Park, also where the Colorado River flows through. And then Glacier National Park within the northern United States, northwestern United States. These are more clear water river systems, both headwater and as well as larger main stem segments like you see here. And then Lake Clark, which is a lake system up in Alaska. So you just trying to provide a broad overview of some of the types of water resources that the Park Service in the United States is charged with managing. I'm going to transition to talking about briefly about some of the climate-driven water resource issues. So broadly, in terms of the climate change that the United States National Park Service has already experienced, Bill Monahan and Nick Fisichella published a study back in 2014, and the results are shown in the map to the left. Basically, what they did was they evaluated the current climate experienced in these places relative to the past century of climate observation. It was 80% roughly of the parks that they evaluated are considered extremely warm in terms of their current climate condition relative to the past century of climate observation. And those are represented by the red dots or polygons on that map. And we often refer to this as the measles map of the US Park Service. We're also experiencing changing hydrology, and this essentially comes up, water as a resource issue comes up in pretty much all parks, whether or not they contain a major freshwater system like a river or a major wetland. Largely, these issues are represented by either too much water in terms of flooding or not enough in terms of drought. We're seeing changes in the form of precipitation delivered to many parks. For example, in the West, transitions from snow-dominated hydrology to rain, changes the delivery of that water. And so this is a major topic of concern. It tends to be in the top 3 for any park we speak to in terms of water resources and water delivery to US national parks. And this, of course, plays out in the socio-ecological system of trying to manage water both to provide for the environment as well as water for people. And this is this balancing act is of course done in the context of climate change. And this is a picture of the largest reservoir in the United States by volume, Lake Mead, which is formed by the Hoover Dam in the states of Arizona and Nevada. And you can see some of the drying in that bathtub ring is represented by the current drought that we're experiencing in the Colorado River. We frame how we respond to climate change using the Climate Smart framework, and we've described that recently in a publication called Planning for a Changing Climate, which is shown here on the left. We published this last year. And in that guide, it shows this climate adaptation cycle. This will look familiar to anyone that's familiar with basic adaptive management cycles, but essentially what we're doing is incorporating climate change into that adaptive management cycle, starting with identifying management goals, assessing your vulnerabilities, potentially adjusting your management goals based on climate-related vulnerabilities, identifying how essentially you're going to achieve those goals using adaptation, selecting amongst those different adaptation strategies, implementing, monitoring, evaluating, and then repeating this process recursively. We like the Climate Smart framework because we find that by breaking this complex process down into these structured elements, it makes it essentially more feasible and translates essentially the understanding of the vulnerabilities into action. How do we actually adapt? And really by breaking this into bite-sized elements, it takes a complex process and makes it doable essentially. And we just to unpack a little bit about the step 2, that assess vulnerabilities. We do that using this traditional exposure, sensitivity, adaptive capacity framework, which is essentially a process to identify and understand vulnerabilities. What's vulnerable, when and where, and why is it vulnerable? And that allows us to, once we understand vulnerability, allows us to design adaptation actions to address that vulnerability. And I bring this up here because when we transition to talking about water balance as a tool, we use that tool to understand climate exposure, so changes in the environment and in the climate, and we pair that with the sensitivity, understanding how the resources are sensitive to those changes in climate to understand the potential impact and ultimately the vulnerability of the systems. So with that, I'm going to hand it over to David Thoma. David will describe water balance as a tool. And David, please let me know when you'd like to advance the slides.
Okay, thank you, Dave. Right, so we use this water balance model to quantitatively assess the resource response to climate change. And so what is water balance? And I'll describe the model conceptually here, even though it's a mathematical model. But essentially it takes precipitation and partitions it into snow or rain, depending on the temperature. If it's cold enough, the water is stored as snowpack, and then when it warms, it melts and recharges the soil moisture. But soil has a water holding capacity that, when exceeded, allows water to either drain deeply beneath the rooting zone of plants, or it can run off the surface to surface water. Additionally, our water balance model tracks evapotranspiration, which is the combination of evaporation from the soil surface back to the atmosphere directly, or through plants via the process of transpiration. So transpiration is an important process because it represents the simultaneous availability of water and temperatures warm enough for vegetation growth. So transpiration really is synonymous with plant growth. However, when the soil moisture draws down, if we don't get replenishing rains, then we incur what's called a water deficit. So this is the amount of water that vegetation would use if that water were available. And interestingly, water deficit is also measured in units of millimeters, just like precipitation, except it's like a bank account that's overdrawn. So just like a bank account deficit is measured in dollars, water deficit is measured in millimeters of water. And it turns out that water deficit is a really important indicator of drought stress. Next. And so this next figure represents changes or the rate of change of water deficit across the continental United States. This is a map created by our colleague Mike Tursek. And what it clearly demonstrates is that the drivers of change vary, the patterns and rates of change also vary. So just like we have maps of change in water deficit shown here, we have change rates of evapotranspiration and runoff as well. Next. And so before we go into the freshwater applications, I want to just reflect for a second on this idea that allowed us to stumble onto this, the value of water balance as a tool for understanding climate change and adaptation options. We began by investigating vegetation response relationships with temperature and precipitation and found that those relationships were not very strong. But when we transitioned to a water balance approach and began looking at it from the lens of evapotranspiration, soil moisture, and water deficit, all of a sudden, these relationships between climate and vegetation response became much stronger and our understanding improved dramatically. So in addition to vegetation condition, we've also used water balance to understand fire risk and drought stress. And as we'll get to in a minute, also, it helped improve our understanding of aquatic resource relationships with climate. But next slide. Just to briefly give you an example of how we use the water balance application in a terrestrial setting. This is a case study from Arches National Park in Utah, which is famous for these really unique geologic features. In this case, this is Delicate Arch. Next. But Arches is not only its arch geologic features, it's also this diverse habitat of shrublands and forests and grasslands. So resource managers there, because they also manage wildlife species and the vegetation, in addition to the geology, might wonder what might be the effect of climate change on these important grasslands, which are forage resources for grazing animals. So using satellite remote sensing, we track the vegetation condition over time and relate it to these different aspects of water balance. And in this case, we found that annual deficit was an important indicator of vegetation condition in this grassland. And you can imagine that as the deficit or drought stress increases, the vegetation production decreases. But we found that there is this pivot point of about 500 millimeters of water deficit, where if we exceed that pivot point, we would expect the vegetation to perform below average. But if we don't exceed that drought stress threshold, then we expect this grassland to perform above average. So using this pivot point concept, which is charted as a heavy black line in the figure, we can relate the historic deficit in this grassland to that pivot point and then model the future deficit for this grassland using two different scenarios. And in doing so, we are able to tell managers what, where, when, and why change might be happening in pretty specific ways. So specifically, the grasslands and arches, when that change might occur. Well, it's probably happening right now based on this relationship. You can see the vertical arrow pointing down to mid-decade between 2020 and 2030. So that helps managers understand the relative sense of urgency for managing this particular kind of vegetation versus other vegetation types in this park, like the shrublands or the forests. And it tells us why this change is occurring. It's because of the drought stress. And that then allows managers the latitude to start thinking about where other vegetation from other drier parts of this landscape might be coming from to inhabit this landscape. And they might even engage in assisted migration if there are exotic species that might overrun this grassland. They might think about transplanting or moving more desirable species that could sustain the grazing resource in this grassland in the future. Okay, next. All right, so shifting gear to freshwater applications, one of the neat aspects of this water balance modeling approach is that it gives us the information that hydrologists are interested in, which is effective runoff, but simultaneously it gives us information that botanists might be interested in, such as the soil moisture, the deficit, and the evapotranspiration rates. If we take the runoff from the water balance model, we can then further analyze it and transform it into what we call drainage functions or runoff functions that are directly related to stream flow that we can measure with gauging stations. And that's what that little figure in the lower right-hand corner represents. Next. So as Dave mentioned, I'm going to mention or talk about a few freshwater applications. Go ahead and advance the next one, Dave. And in this case, this is our colleague Andy Ray, who's monitoring amphibians in Yellowstone National Park. And Andy has been an early adopter of this water balance approach to try to understand how climate might affect the amphibians that he monitors in a place like Yellowstone and Grand Tetons. Next. So working with another colleague, Megan Halabisky from the University of Washington, Andy has found that the wetland area can be very effectively measured using the Landsat satellite time series. And then when we combine the area of wetlands measured from satellites with the water balance modeled runoff, we see these very strong relationships emerge, in this case with an R-squared value of 0.84. In addition to the strong relationship, we can be pretty quantitative in our assessment of how modeled runoff changes the wetland area. In this case, for each additional millimeter of runoff, we see this wetland for this one location that's monitored in Yellowstone change by almost 400 square meters. So it's a very responsive or sensitive wetland to changes in runoff. Okay, next. So in this slide, we're looking at a time series of photographs taken on an anniversary visit date. So this is in early July from 2007 through 2018. And you can see there's a large variation interannually in the area of surface wetland expression that's a function of the weather in that particular year. And Andy and his field crews have also noted that the abundance and diversity of amphibian species is linked to the area of habitat that's represented by this surface water expression. So the figure in the top right shows wetland area on the y-axis and time on the x-axis. The gray line shows the variation measured from the satellite, which is reflected in the photo series on the left. And you can see the blue dots represent a high abundance and diversity of amphibians in this wetland. The brown dots, when the wetland area is below its average condition, represent a below average abundance and diversity of wetlands. And if we take these relationships that I showed in the previous slide and model them into the future, we can see that the expectation is that the wetland area is likely to decrease over time. And this has important implications for these species in this particular wetland. So Andy and his colleagues have taken this idea and applied it to every wetland in Yellowstone. This is over 600 wetlands, and they characterize these wetlands as ephemeral. This is the figure in the bottom here, as ephemeral, intermittent, semi-permanent, or permanent, and they've described the sensitivity of these different wetlands to variation and runoff that we can then model into the future and use those relationships to understand what the ultimate impact might be on these important species that are both important due to their intrinsic value, the diversity that they bring to habitats like this, but also because they're relatively low on the food chain. And as Andy Ray has said, just about everything eats amphibians. So these are an important food resource for higher level predators. Okay, next. All right, so shifting just a little bit to the Lamar Valley in Yellowstone. This is what's often referred to as America's Serengeti because it preserves the full complement of predator and prey species. So this is the American bison. This habitat also supports grizzly bears and wolves as well. Next. In addition to the native ungulates and their predators, this is an important river system. It's a very important cutthroat trout fishery, which is a species that's endemic to Yellowstone and a very popular fish for fishermen to chase. So we might think about what are the consequences of climate change on this particular river system. And if we try to model this river flow with precipitation, we see that the relationship between precipitation and modeled flow is not very good. And that's in large part because most of the precipitation here falls as snow in the winter and it's not providing river flow until it melts in the spring. Next. So if we shift our thinking to the water balance applications and model runoff from the water balance and compare that to measured flow, this relationship improves dramatically. Next, go ahead and go to I think the second, yeah. And we can see that there's a relatively strong relationship between the time series of modeled flow on the river versus the measured flow on the river versus the modeled runoff that we get from the water balance. So when we have relationships that are of this high quality, this strong, it gives us the confidence to make future projections. Next. And that gives us the information that we need to start thinking about what the implications of climate change might be. Go ahead and show the next figure, Dave. And what those implications might be for this river in the future, which gives our managers a big jumpstart in terms of planning. And so we've already used information like this in planning projects with our aquatic ecologists and hydrologists in Yellowstone, who are actively engaged in cutthroat trout restoration and maintenance on this river system. So as you can see, the implications are pretty clear under these two future scenarios. It looks like the projected river flows might decline to such a rate that the models suggest that the Lamar River might become an intermittent stream in the summertime, and that would have dire consequences for these native fish that rely on consistent cold water from snowmelt. Okay, so I'm going to turn it back over to Dave at this point. We'll talk about some infrastructure topics.
Thanks, David. Yeah, so I will just briefly cover one example of using this sort of water planning framework related to infrastructure within Big Bend National Park, which is a national park that straddles the U.S.-Mexico border right along the Rio Grande. And specifically within Big Bend National Park, I'll focus on this Chisos Mountain developed area. You can see in the middle ground of this picture a restaurant and hotel, as well as a store, and all of the infrastructure within Big Bend National Park. This is within the Chihuahuan Desert, relies on a desert spring, a shallow groundwater spring that occurs in the desert floor. Basically, all the water that provides essentially all the services within this area of Big Bend National Park is provided by the shallow groundwater spring. And the spring is about 70 years old, and the park is looking to rehabilitate the spring or potentially switch to a different water source. And they came to the Climate Change Response Program and asked, what are the projections of precipitation for this area? Primarily, their interest was related to their observations that this spring is sensitive to changes in contemporary precipitation. And so we started by evaluating how spring flow from Oak Spring, the spring that I showed you, is related to precipitation. What we found was that indeed, when there are spikes in terms of the precipitation, which is shown, that ultimately results in a lagged response from this shallow groundwater spring in terms of its flow, and that's the black line with the red dots. So we can see that indeed this spring is responsive to changes in contemporary precipitation. So climate change is going to have impacts in terms of the amount of water that's generated or comes flowing out of this spring. And using a combination of information from hydrogeology as well as the water balance model, what we discovered is that the spring is responsive to changes in precipitation, but not temperature. We started by anticipating that the interaction of those two may be important, but ultimately, from a variety of scientific resources and understanding, we essentially believe that this spring is fed directly by in the bedrock geology in the recharge zone of this spring. And so any changes in precipitation will result in changes in spring flow. And just to note, the park itself is really interested in this 20 gallon per minute threshold, and that basically anything below 20 GPMs, that's the dashed line that crosses this, is going to be a water management challenge for the park. You can see that this has occurred in various time periods, back in 2011 to 2012, 2013, as well as 2016. And when there's not enough water, that forces the park to undertake a variety of conservation measures, including shifting to basically disposable cutlery and plates within the restaurant. It challenges fire prevention operations within the park, within this region of the park. And so I'll skip over a lot of the scientific detail, but by understanding the relationship between precipitation and flow, and then by basically projecting future precipitation using global climate models, we were able to evaluate how often the spring is likely to drop below that 20 gallon per minute threshold of interest. And so we looked at historically the number of months per decade that occurred, compared that to two different climate futures, a warm, wet climate future, dry climate future projected out to 2065, and found particularly in the hot, dry future, there would be more than a doubling of the months per decade when this spring dropped below that threshold of management interest. And so the park is using this information to develop adaptive management strategies or adaptation in both in terms of increasing the amount of water storage that they have. So they're going to double the amount of water storage they have in tanks that store this water to be able to provide consistent water availability through even some of these tougher drought periods that are increased variability, and then do other things to increase just water conservation in this part of the park. So that includes things like changing over to low flow toilets or heads, and increasing water conservation within the restaurant itself. So just to bring us back to the Climate Smart framework, we provided some examples of using the water balance model to evaluate exposure and sensitivity, ultimately to understand vulnerability of a couple different resources. We're doing this in a broader array than what we showed here, but we just wanted to zoom into a couple examples, both in the natural resource domain and in the infrastructure domain. It may seem like we're much because we've largely focused on this vulnerability assessment, but this ultimately, this understanding of vulnerability is the foundation to essentially set climate-informed goals, as well as identify the appropriate management strategies or adaptation strategies that we can deploy to achieve those goals. And just to, one of the real benefits of water balance is that it allows us to actually do quantitative assessments of vulnerability, and we couch this within the Climate Smart framework because essentially, once we understand, essentially this allows for us to place the research and science that we do within the management, the important management context, and create a clear linkage between our goals and the actions that you pursue to achieve those goals, informed by science. We can do this using vulnerability assessments. In many cases, we have to because we don't have the quantitative information. But to do so, we have to rely on good professional judgment, and it suffers from the classic problems of sometimes personality-driven judgments about what's sensitive and what's not, and how the sensitivity plays out. You could just be wrong ultimately. So where we can, we really prefer to engage in these kind of quantitative vulnerability assessments, and water balance is a really great tool to do so. It allows us to identify these more proximal climate drivers, increase our accuracy, and reduce our uncertainty, both in terms of, we didn't show this, but we can use water balance both in terms of near-term nowcasts of water deficit, water availability, as well as longer-term future projections of changes in water across the landscapes. And using this tool, we essentially have been improving it through time as we deploy it in different applications. And ultimately, I think using this, we can increase our credibility in making science-informed management decisions. And with that, I will thank everyone and hand it back over to the organizers.
Okay, thank you, Dave. And David and Eddie, really appreciate you taking the time to put together very informative presentation, such a range of challenges and tools available. I invite anyone on the call to post a question in the comments. You can also unmute your phones if I call on you and ask your question out loud. We had a little bit of conversation in the chat while folks were presenting. Titus asked a question about bioremediating tools to address the eutrophication of those water resources. And Eddie did respond in the chat. Eddie, do you have any other information you want to share on the phone? to respond to that question?
Yeah, thanks, Melanie, and thanks, Titus, for the question. Yeah, I think in those particular case studies I mentioned, the volumes are just so significant that I'm not aware of any technology. But in smaller systems, smaller dams and so forth, you do get things like what in South Africa called eco tabs. They're like microbial tablets that you put into the water body that suck up the microbes and create an oxygenating environment. But in those particular cases, those dams are about 3 billion cubes of water. So, they're bigger than the kind of Hoover Dam that you have in the US, just for comparison. So, yeah, when we had those particular challenges, we weren't able to source any technology that could assist us. But moving forward, we definitely need to look at some kind of options. But ultimately, it boils down to having the governance systems in place and making sure that water is treated on site and doesn't become a problem downstream. Thanks.
Okay, thanks, Eddie. There was also a bit of conversation from Larry that Eddie responded to related to sort of systemic adaptation strategies in the river basin. Is there any other information you want to share on that?
No, not really. At this stage, it's just one of those programs we're really hoping that will kick off. I think, as I mentioned, CASA, which is the big protected area between Botswana, Namibia, Zambia, Angola, and Zimbabwe, is really taking the lead in terms of linking with the two river basin organizations there, OPRACOM and ZAMCOM. And I think because they're servicing a much larger constituency downstream. But I definitely think we really have to start pushing in that direction. I'm aware that RBOs are aware of some limitations in themselves in sort of doing this broader systemic approach. And I think because we share this footprint at regional levels, there's definitely complementarity. And I think the future is bright in that respect in terms of looking for that cooperation. Thanks.
And I'll just share, I put in the chat a link to a really interesting article that provides kind of a conceptual framework for understanding distinctions in different sort of scopes and scale of adaptation strategies, moving from inaction to coping to incremental adaptation to transformative adaptation, which looks at systems as a whole. So Eddie, your comment about the Transfrontier Conservation Area working with the river basin organizations sort of triggered my thinking that this is a great opportunity for looking at ways to, or strategies for transformative adaptation that goes beyond mere sort of single factor responses, if you will. So recommend that for folks who are interested. Thank you.
Yes, thank you, Larry. Thanks for posting that in the chat. We will include that in the follow-up email as well. Joel has another question for Eddie. Joel, do you want to unmute your phone and ask him yourself?
Sure, if I can find all the appropriate buttons. Hi, Eddie. You were talking, in the adaptive management framework, you were talking about the importance of the thresholds, and that you actually, at least for South Africa, you have, in policy acknowledgement of ecological flows. And so I'm wondering if the conversations have got to the point of how, readjusting what those thresholds might look like in light of future climates. Or maybe it's just a matter of maybe the flows remain the same, the goals for the flows remain the same, but readjusting the strategies on how you're going to achieve them.
Yeah, Joel, it's a very interesting question. I think whilst we've had these environmental flows in theory under the National Water Acts in the region for about 20-25 years, they've only really been put into place and gazetted formally in the past 5 years or so. So we've been steadily implementing them from the Kruger Park's perspective with our water sector partners. So that's been about a 10-15 year process. But certainly I think with the new climate change driven forced hydrology, we are starting to see that that the forecast hydrology does show you that we are going to see a big reduction in mean annual runoff in some of our catchments. And also the demands are going to increase. But having said that, we need to maintain a certain scalable capacity in rivers. Our rivers are, for the most part, have already been compromised. We've lost a lot of sensitive species. And what that also means is we've lost a certain amount of ecosystem services from water quality assimilation and those kind of things. So to shift the goalposts immediately would be, I think, well, not right. I think what we have to do is demonstrate that we're proving the hypothesis around what environmental flows are intended to deliver. And then, yes, we can maybe have a look at those questions later on. But ultimately, when we argue for those, we're not talking about it specifically from a ecosystem-based perspective. We always give the rationale that this is about a social ecological flow rather than purely an environmental flow. Thanks, Joel.
And thank you, Eddie. We have another question. This one's for David and Dave. I'm just going to call you David and Dave. As she asks, what are the data requirements for using the water balance tool? It seems really useful, but wonder to what extent it can be applied if no local data is available. Can data be derived from global data sets or by other means?
Yeah, this is David Thoma. I'll take that one. At a minimum, we need temperature and precipitation, but you can run the model using more complicated methods for calculating potential evapotranspiration if you have the data, like relative humidity, wind speed, and solar radiation. But again, temperature and precipitation are the minimum requirements. And if you have that from a weather station, you can use that. Or if there are global data sets that might be relatively coarse resolution, 12 or 30 kilometers even, you can use those as well. The neat thing about the water balance, I guess I would point out, is that even if you use a really coarse spatial scale data set, like one of the global models that might have a 30-kilometer resolution, the water balance allows you to model variations in things like soil moisture that are a function of the soil properties within that grid cell. And it also includes variances for slope and aspect. So if you have a south-facing hillside in the northern hemisphere, that's hotter and drier than a north-facing hillside. So I think it's reversed in the southern hemisphere. But again, the model accounts for those kind of variations within the temperature and precipitation grid cell if all you have are the really coarse resolution data.
Okay, thanks, David. We are out of time. That's all the time that we have for today. So I'm going to go ahead and close this. We will send a follow-up email with this webinar recording and slides or link to them, as well as the chat and the questions that we've shared today. So thank you very, very much to Eddie and David and Dave for joining us, and for our hosts and our audience. I really appreciate you taking the time. Real quick, I want to announce next month's presentation. I'm going to very quickly share my screen, or very slowly, one of the ways.
Oh, I think I did.
Oh, you got it? You got it, Joel. Thank you. Okay, wonderful. Okay, next up, at the end of March, we are doing this webinar series at the last Wednesday of every month. So please plan to tune in. Scenario Planning for Climate Change Adaptation. Our speakers are Dr. Gregor Skierman and Dr. Brian Miller. We will send information on this session and the follow-up email, as well as a couple of weeks before the actual session. I hope to see you all there. Any other closing comments from anyone?
This is Joel. Just to thank everybody again for joining in, and a special appreciation to the speakers for presenting today. That was really wonderful.
Absolutely. Okay, well, now I'll go ahead and close this session, and thank you again.